Okay, so you'll see a little bit of this. At least I can go forward. So yeah, this is the spoiler I was telling you about the word neuromorphic. And the initial part of the presentation is about how the word neuromorphic now is being used to represent many, many different things. And so because everyone has their own definition of neuromorphic, I also copied from Lewis Carroll's definition. When I use a word, Humpty Dumpty said in another scornful tone, it means just what I choose it to mean, neither more nor less. So you'll see what I mean when I use the word neuromorphic. But just to give you to explain why I'm using this, I'm arguing about the word neuromorphic is just to tell you that uh, it has many, many different meanings. It means something very, very clear to the people that have been following Gert's lectures and to Gert and me and to Terry. But in the 2008, there was this discovery, let's say, made that led to the discovery of a new device that actually works as a synapse. And because it works as it has memory, non-volatile long-term memory, it actually has a lot of interesting physics. It has state dependence, intrinsic stochasticity, and because it's being used to store memory by adding pulses to the bottom and top electrode, it has been resembled to a synapse. And so, you're doing electronic circuits, you think of synapses, you can use the term neuromorphic. So people doing memristor are actually using the term neuromorphic to refer to these devices. They're device physicists, material engineers, and whenever they think neuromorphic, they think memristors. Then around the same year, the DARPA Synapse project started and proposed to use a lot of electronics to build simulators of neural networks. And so in 2014, the True North chip was designed by IBM and colleagues, also from Caltech, from Kodena Boine and Rajit, to simulate crossbars of synapses that would then send spiking neural networks to neurons that would integrate them, and then they would produce spikes in output. And it was an amazing chip. It was designed only once because it was huge. It was the biggest chip that the Samsung foundry ever made before and after. It had 4,000 of these cores, each core 256 neurons. So it's not being used so much anymore, but it still has 1 million neurons. These 4,000 cores work in parallel. So it's a massively parallel system like the brain. But each one of the neurons inside the core is numerically integrating the state equations through serial processing. So it's a mixture between von Neumann architectures that we mentioned, where you have one unit that just clocks through time and integrates the numerical equations, and you have 4,000 of these working in parallel. I should also point out there is no clock, it's asynchronous. So it just runs the equations as quickly as it can. And whenever it's finished, every core runs in parallel with their own self-clocked steps. And then every 1 millisecond, then there is a manager that synchronizes everything and sends the spikes from core to core to make sure that time in each core is aligned. Physical time is not considered here. This is a simulation. So simulation time can be much, much faster than physical time, or maybe it could take hours to simulate, a protein folding, which in biology would fold in a few milliseconds. So here, this is a simulation, but still, because it's electronic, it's spiking neural networks, people use the term neuromorphic to refer to these types of systems. And now that we have the AI revolution that Terry mentioned, there is also a lot of people starting to use the term neuromorphic to refer to spiking neural network simulations, even if they're run on a standard von Neumann architecture on a computer or on a GPU. So the term neuromorphic started to lose its meaning. Everyone was jumping on the bandwagon of neuromorphic because it also provides funding. It has been for some years a very sexy term. And so the meaning of the term neuromorphic really got diluted. This was sort of the controversy or the provocation I wanted to give when I said why I'm going to use my own meaning, because otherwise you don't know what I'm referring to if I just say neuromorphic. And now that the AI has become so popular and there's the AI revolution, we start to see people jumping off the bandwagon of neuromorphic and to focus more on just AI and Adore. AI. And I should say I use this provocation to tell you what do I mean, and I was saying Gert and I and Terry, what do we mean by neuromorphic? It's what was actually originally proposed by Carver, Mead, and Misha Mahowald in the late 80s, early 90s. And so if you go and look at the proceedings of IEEE from 1990, you will find the paper where the term neuromorphic appeared for the first time ever. And this is what Carver wrote in that paper. The fact that we can build devices that implement the same basic operations as those the nervous system uses leads to the inevitable conclusion that we should be able to build entire systems based on the organizing principles used by the nervous system. I will refer to these systems as neuromorphic systems. So basically the idea is any electronic system that uses the same organizing principles of the brain, according to this definition, is a neuromorphic system. But then if you also go and so look under the hood, like Terry was saying, of what they were actually proposing, they were proposing to use CMOS electronic systems. We're using subthreshold analog transistors. And in subthreshold, the transistor is producing current because of diffusion. It's called weak inversion, and the majority carriers across the transistor channel go from one side to the other because of diffusion. And if you know about sodium and potassium, and you know how action potentials are generated, it's exactly the same physics. You have Boltzmann statistics, exponentials, and therefore you can reproduce the same physics, even though it's a different medium, with CMOS transistors. And if you have the equivalence of a sodium or potassium channel with an electronic transistor, you can imagine once you start to put transistors together, you get equivalences also at the macroscopic level. If you create a neuron with many of these transistors, you will have a hard time distinguishing the response of the neuron to inputs from a biological one and a silicon one. And this was really the discovery or the breakthrough that Misha and Carver made in those years. And from those years on, at Telluride and around the labs that were working on this, there's been a huge amount of progress in building silicon retinas, silicon cochleas, artificial silicon neurons, synapses, and you'll see some examples also today, and this progress is going on. This in parallel with all the others that you saw, with the memoristic device community, with the neuromorphic computing community, with the matrix multipliers in memory computing type of activities that are also using the term neuromorphic. And the provocation is that, you know, the way that Misha and Carver proposed it, it was the same philosophy that Dick Feynman had when he was there at Caltech. I'm doing this because I'm interested in basic research and just understanding, and I'm using the physical system as an additional tool, in addition to experimental neuroscience, theoretical neuroscience, computational, to try to understand how the brain works. It was really basic research. They did not have any specific application in mind or any startup in mind at the time. Whereas typically, not always, but typically the standard AI workloads are top down. Like, I want to solve a problem, I'm going to use, you know, I'm going to train a neural network to solve the problem. And then if it works well, then I can even make money out of it. I can even sell it. So typically they are serving different purposes, and with the old school neuromorphic is really useful for basic research, where, as you know, the standard AI approaches are extremely very, very useful and powerful for more applied type of research. And what we do in Zurich still follows the tradition of what we were doing at Caltech. Zurich now was actually founded by Misha Mahowald, together with Rodney Douglas and Kevin Martin, and now has also Toby Delbruck and Shichi Liu, who were the students of Carver, together with me and Jörg Kramer, who unfortunately, also Misha and Jörg unfortunately passed away several years ago. But we do follow this tradition, so we try to understand how the brain works. It's basic research. So we do have neuroscience. There are people working with monkeys, zebrafinch, rats, until Kevin was there, cats as well. So there's a lot of experimental neuroscience. But we also, of course, have to build electronic circuits. So we use microelectronics, physics. We try to exploit the physics of these devices to carry out computation. We don't discretize them to zeros and ones and then use von Neumann architectures. But most importantly, we compute through time. We let time represent itself. This is what also Carver was saying. So this is really the big important factor. If we have systems that do, you know, these dynamical systems that carry out solve equations, they do that through time, which can be an advantage or disadvantage, because if you're trying to simulate evolutionary processes, you have to wait evolutionary timescales. So silicon can actually be quite slow compared to what you could do with a GPU if you just wanted to explore parameter space 1,000 times per second or something like that. And then you can't expect that, you know, you build a chip, you put it on a desk and you say, oh, it's intelligent. You need to have some inputs to the chip and you need to produce it behavior. The only reason we have brains is to produce behavior. So then we also see if these chips that we build can have emergent intelligence coming out of them. We can do that if we have sensory inputs and motor outputs. So we connect them to actuators and we send inputs to them. Yeah, the idea is that if we want to understand the brain by building it, we want to stay as close as possible to the biophysics using these analog circuits. Having said that, I'm not saying that we should not use digital. Digital is also very powerful, and the best is to use the best of both worlds. So the idea is to use digital wherever you can, but if you can also use analog, that's just one extra degree of freedom or one additional tool that you have to do even better. So just to make it clear that it's not analog versus digital, it's just that in addition to digital, you can have benefits if you also use these subthreshold transistors. And I don't need to convince you, but there is an existence proof that if you use these subthreshold analog devices like real neurons, you can get very, very low power and you can get very far with small networks. You don't have to build, you know, terabytes of data in networks that have thousands or hundreds of thousands of neurons. Even a few neurons get you really, really far if they are connected in a recurrent way, in the right way, if they have the right synapses, the right structure. So even small computing systems with less than 1 million neurons can actually do, you know, pattern recognition, fine motor control. They can do reasoning. They have these have language. We were talking about dances, and the different types of dances have different meanings. They can dance to rhythm, or they can produce rhythms. So it's not necessary to think of huge, very large scale to have something interesting. Even using something that, you know, we can easily put on a chip, you can get really interesting behaviors out of it. And in addition to that, it's possible to get interesting and fast behavior by using slow and noisy elements. So that's something, again, that in digital isn't obvious. Of course, you could simulate noise, you could simulate variability, but it doesn't come natural to do that. And we have to deal, if we build these chips, we have to deal with the variability and the noise of the analog circuits. And we try to slow them down to the same time constants of the signals we want to process. So we process at the data rate. Terry was saying information is feasible, or no, it just goes away. I don't remember the word you used. I wanted to write it down, but it's sorry, but the information just passes through and
Flows?
no, it's another one, but it flows through and then it goes away unless you have a way to store it. But in this flow, you're actually processing it. So if you can process the data at the same data rate as it's going through, if you can resonate with the data, then you get a natural processor that does not need to transfer data back and forth from the memory to the CPU, like in von Neumann architectures. And you can save power in doing that. So that's why having slow elements can be useful, especially if you're dealing with slow signals like biosignals. Of course, wiring is a problem both in chips and in the brain. So having small world networks and local connectivity is important. Not having just 32 processors, but 10 to the 11 like we have in our brain, or hundreds of thousands, is also something that should be done if you really want to stay close to biology. And of course, if we need to deal with noise and variability, we need to have this learning and negative feedback always on. So this is an important ingredient for this recipe. We then can use this to do real-time spatiotemporal processing in closed loop. So that's the other thing. And the importance of time represents itself is also highlighted here, that the brain uses the evolution of physical systems to implement its computation. So you're really computing through time. This is something that is not obvious to computer scientists, where you just have t plus 1, t plus 2, but it's completely detached from physics and physical time. And so following this recipe and trying to use these principles, the principles of neural design, we have been building these types of chips for many years. This is a very old example of a chip, but you can see on the side here, we have some building blocks which implement physically a spiking silicon neuron. So you can see the membrane capacitor here, and then you have transistors that, when there is current flowing, they change the voltage. If the voltage exceeds the threshold, then they produce a digital pulse, and then they reset and they keep on integrating and so on. And what we do is we create the layout of the circuit, and then we copy paste it as many times as we can. And the same for the synapse. The synapses also are not just multipliers like you would have in a deep network. They actually have their own temporal dynamics, and they have their own nonlinearities. If they're short-term depressing synapses, the weight changes with every spike. If they have learning, the weight changes with the conditions, the pre and the post, and maybe the calcium variable or the calcium concentration that could be stored on a capacitor. And so then we can also copy paste those synapses. So now if you think about it, you have a huge synaptic matrix that is an intelligent synaptic matrix within memory, with memory, because every synapse has its own local memory storage, its local calcium buffer. And then you have a bunch of neurons that are connected to the synapses, but are completely disconnected to the others. They're fully dissociated. So the question is, how do you create networks having this culture of cells in silicon that have the right dynamics? And the trick to do that was also invented at Caltech by Misha and colleagues, is to convert the output into digital words and then to use lookup tables. You can use digital technology. FPGAs were mentioned, but just memory buffers. Whenever neuron number, you can see it here, for example, if neuron number 3 spikes first, if neuron number 3 spikes, then you can put the address on a digital bus and send it to a destination, which will decode it. And whenever any other neuron spikes, you just put the address on the bus at that time in which it spikes. So this is called address event representation, AER. And then once you have this digital, you could think of these, for example, as pixels of the left retina. Then you have pixels of the right retina. You can send those through two virtual nerve fibers to a orientation detection chip. And then you could just connect those to the first neuron could be looking for vertical bars. The second neuron could be looking for horizontal bars, and so on. And you can imagine of building a complete visual system just by sending spikes from chip to chip, or in the case of multi-core chips, from core to core, like in the true north. So that's what I was saying. You use the best of both worlds. You use slow analog circuits for the dynamics, and then fast asynchronous digital circuits for the connectivity, for routing spikes. And the connectivity is programmable because it's digital. You can actually change the addresses to connect any neuron to any other synapse. So this has been really a great advantage. We've been building these types of chips for many years. This is another more recent one where you start to see multiple cores. Each core has 256 neurons in this particular case. And if you just zoom in one of these neurons, it's actually a bunch of synapses connected to the neuron. And if you look, the analog circuits are only a tiny, tiny fraction of the area. So they're maybe less than 20% of the area. The rest of the area is occupied by memory. These addresses that I told you that if you program allows you to connect neurons with, among each other. And so most of the area here is dominated by the digital memory that is needed to connect synapses and neurons together. And this is really the biggest drawback of this approach, because like Toby always says, if you want to scale these things up, if you want to have 10,000 neurons, then you need to, instead of having this, let's say that this is, 1 by 1, you need to have this 3 by 3 or 3 point something by 3 point something. So you need to really increase the area of the silicon. That's why the true north chip was so big, because every neuron takes up, or every core in their case, takes up physical area. And when you fabricate chips, area is what matters. You pay by the amount of area in silicon. And so this type of technology doesn't scale very well if you want to do very large networks. It's good for relatively small networks. This is like 1,000 neurons. Maybe now with more advanced processes, you could do 10,000 neurons, but definitely not the size of a ChatGPT network. However, there is some promise, there is some potential, because these memristive technologies that are being developed, these memristors, they are 10 by 10 by 10 nanometers. And they have a long-term memory. Once you change the conductance, you don't need to power them up. So you could replace these 12 transistors per row with one of these 10 by 10 nanometers. And so you could really scale things up. In addition, Gert actually has a really nice paper together with Stanford. You could even go forward in that direction and build in 3D. So with 3D VLSI technology, there is a very nice paper also by Kwabena Boahen from Stanford that shows that following this approach, you could really build volumes of spiking neural networks with synapses that don't melt themselves, because otherwise the heat would be so, if you don't use this approach, the heat would be so big that as you make things bigger and bigger, the temperature would just start to melt everything. And so Kwabena has the recipe for using subthreshold analog in 3D that grows with a factor that is less than the heat, in which the volume grows with a factor that is less than the heat. And this is the solution. This Carver-Meads type of neuromorphic is the solution, together with the memristors to replace the memory. So the other thing that is important when talking about chips that have noisy elements, remember all of these analog circuits, even though they're identical when you copy paste them, when you fabricate them, there will be slight differences. And so every neuron will be slightly different from every other. I will show you. In order to do robust processing with noisy neurons, we've heard over and over this morning and this afternoon that it's important to think about representations. The code is distributed. Each single neuron actually represents only one small piece of the total information. And the representation, again, is something that in standard AI is not discussed or explored enough, in my opinion. It's not just having an analog variable on a ReLU function. You really need to think about representing even something as simple as an oriented bar by having populations of neurons acting together. And then if you go in this direction, you will quickly find out that there are tuning curves. A neuron is not just selective either only to one thing and nothing else. It will fire a bit less if you have a stimulus that is a bit different from the optimal stimulus. And by combining all of these neurons together, you get populations codes, which have been shown to be, Bayesian optimal and so on. And this is just to show you that if you put the same types of neurons and you connect them in the same way from the anatomy of the visual cortex on our chips, you get the same type of tuning curves. In fact, if you only had the feed-forward connections, that would be the green plot. You get a bump because you have a bump in input, you get a bump in output with some noise. But as soon as you turn on if you connect them like in the cortex with recurrent excitatory and inhibitory loops, like a winner-take-all network, you see the sharpening of the tuning curve, and you have selective amplification. You selectively amplify the preferred stimulus, and you suppress the noise or the non-preferred stimuli. It's just a matter of the dynamics of the networks. We didn't engineer it. We just connected the neurons in the same way that anatomy or Kevin Martin told us from his experiments in anatomy.
So Giacomo, the figure at the top is real experimental data from Hubel and Wiesel.
From Hubel and Wiesel.
1968. That was
what led them to the Nobel Prize, basically.
That was the insight that led them.
Yeah.
But one of the things that you see there is that even though it's real data, it's actually almost as good as your neuromorphic data, right? And but
by design.
Also, isn't it a problem with neuromorphic circuits that you do have to worry about offsets and things that are?
Yes, that's exactly the point. So because of these offsets, you cannot, I would never use a neuromorphic chip to control my airbags or to do my bank accounts, for example. But you can get away with it if you use populations, which is a price that you have to pay, because in addition to having to pay area, if you want more neurons, you have to make bigger chips. You have to start to use more neurons, or to have one of your ReLU units, right? You have to use 10 or 20 neurons to represent a single robust ReLU unit, because then you can average. You can do your sort of statistics where your variance goes down with the square root of the number of neurons. Actually, Surya Ganguly from Stanford showed that if you have EI networks with nonlinearities, the variance goes down with n, not with square root of n, which is much, much stronger. So in the end, you don't need too many neurons to average out the noise, but still you do need 8, 16 neurons to have a, a variance of less than 0.1. Yeah, that's exactly the point. So see here, for example, in our core, we have 256 neurons. We inject exactly the same current to all the neurons, and then you'll see some fire earlier, some fire later. So they are noisy. We don't try to reduce the noise through brute force engineering techniques. We just design them, without trying to minimize the noise. But we do get this variance. This coefficient of variation here is about 0.2. And if you look at the FI curve, so we send spikes in input to their synapses, we measure the spikes in output from the neurons, you see they're all over the place. That's why I would never trust any one of these neurons to control an airbag. But once you start to put all of them together, you get a really nice mean response that is quite linear, like a ReLU. And the inset here, this is data from real cortical neurons. So you can see that they're not so far away. And so, yeah, that's why I was saying if you use populations of neurons rather than single neurons, then you can get away with the fact that they are noisy. These are noisy. So that's basically what you need to do if you want to have reliable computation. The other trick is to use learning. You can learn away the mismatch, and I'll show you, we do have learning circuits, but this is a very powerful already strategy to reduce noise. And we quantified that. We said, if you have one single neuron, you have a coefficient of variation of 20%. What about if you have clusters of 2 neurons or 4 or 8 and so on? And by increasing the cluster size, you can reduce this coefficient of variation. Once you have the coefficient of variation, you can convert that into equivalent number of bits. So for computer scientists, it's nicer to think into equivalent number of bits. And the color code shows you here the equivalent number of bits. So if you want an 8-bit accuracy, you need to have a population of 8 neurons and maybe integrate over 50 milliseconds to get that accuracy. You cannot go to 32-bit floating point. In this case, with 256 neurons, if you use all the core, you get 14 bits, but you do have some limitations. Yeah.
So, the latest AI chips, which have been optimized for these deep learning networks, only have like 8-bit accuracy.
Yeah.
So, they discovered that you don't need 32 bits.
That's the strategy to reduce power consumption, because AI has this power consumption issue. So the strategy is reduce resolution, reduce memory, and that's all pointing in the same direction of what evolution found, by in building brains, in biological brain. Yeah, Olivier, you have a question.
Yeah, you're saying that they're noisy, but are they noisy relationship to each other or to itself?
That's a good question. So no, the most of the noise is basically fixed pattern noise. It's device mismatch. So every neuron, if you give them the same input, they will have different outputs. But if you repeat the same experiment 2 times, you will get more or less the same, unless the temperature changes in between experiments. But if you repeat them 2 times, you get more or less the same output. So it's the noise in time is very, very small, but the noise across space is very large. So it's device mismatch, which is a quenched noise, if you want. It's fixed pattern, and once you fabricate the chip, you have it there.
What magnitude of temperature change are you talking about?
So it depends also on what you design. So if you don't do anything, then the temperature actually has a huge effect. If you change only by like 2 or 3 degrees Celsius, you will see that there is a variability of also there in that range of 10-20%. But what we can do there, we can use engineering techniques. We can have temperature compensated bias generators. So on the side of the chip, you could put something that compensates for temperature changes, which regulates temperature like we do in our body. And then you remove the dependence on temperature by having some brute force engineering. Yes.
Isn't noise a good thing from time to time?
Yes. Thank you. It's the next slide. So so once you have populations of noisy neurons, they have to be noisy. You can actually demonstrate both through theory and through experiment that the population response is much faster than the response of a single neuron. You intuitively you can imagine that you have many neurons that are at different states, and whenever you give a kick to the whole population, the ones that are closer to firing will fire soon, and the ones that were far away from firing will take longer to fire. So the population response is faster. And the theory, it's called time encoding machines, both from the US, from New York, or Lazar, and from EPFL, have shown that if you have band limited signals and you have band limited neurons that can, for example, you have a signal of 1 kilohertz, but your neuron can only fire at 40 hertz. If you connect n neurons together, you can increase the bandwidth of the population by a factor of n. So you can encode fast signals with populations of neurons. It's been demonstrated by Tatiana Tomachenko. She showed that if you have a population, you can really speed up by a factor of 50. And it's obvious if you think about the vestibular system, where you have factors of acceleration that are much, much larger than the dynamic range of single neurons. Only by having populations of neurons, you can actually encode these acceleration factors. But they have to be noisy. Imagine if they're all always the same and they always go synchronized up and down, having 1 or having 100 doesn't make any difference. So on a GPU, unless you explicitly add noise through some software algorithm, this wouldn't work. In our chip, noise actually helps in this respect. Another myth is that neurons need to fire at high firing rates in order to be precise. This is also not true, and in this case, it's been demonstrated by Christian Machen, Sophie Deneuve, and many others, that if you have recurrent networks, you can train them you can put as the loss function sparsity. You want to maximize sparsity, and you can train them to encode precisely any signal or produce in response to any signal, any output, with a very, very low average firing rate. So they can be very, very slow, and they can have a very small reconstruction error through training without having to fire at very high rates. So this is also a false myth that you can have high accuracy with very small number of spikes per second, provided you have a population. If you have only one, of course, you will lose a lot of signal. Another myth that was falsified by Van Rossum is if you have deep networks and you want to transmit information across all the layers, you need to have noisy. Not only it's useful to have noisy neurons, it's necessary. It's a necessary condition. And this was demonstrated if you have many spiking neurons that are receiving weak inputs and strong inputs. If they're bit precise identical, they will tend to synchronize. And in the end, you only transmit the highest energy and you lose all of the details in the small signals. But if they are noisy, then through averaging at the last layer, you can recover the information, also the small changes in the information that was in the first layer.
How changed with the use of different kinds of protocols?
In this case, I think they are sending Poisson spike trains across. What is that what you mean in terms of protocols?
Yeah,
or
yeah, because you transmit some signals, some communication with one point to the other point, right? And then you codify the input signal, and then consider.
So here it's just talking about sending spikes. So the way that the signal is encoded, if you have some analog waveform like a biosignal, it's possible to use an adaptive neuron to do a sigma delta type where you look for changes, or if you just send directly the current into the neuron, you do pulse frequency modulation. So the rate of spikes increases if the amplitude of your signal increases. So that would be pulse frequency modulation. Or you could look at how the change, and that's true in biology as well. We have transient responses or sustained responses for the neurons. We have, the mechanoreceptors can be looking for static or derivatives. So we can do that also with the circuits by using adaptation or just by sending signals directly into the integrate and fire neuron. Yeah, but then once you have spikes, this is all in the spiking domain. And if you have noisy neurons, you get all these added benefits. So we do pay the price of increased area. We need to have populations of neurons to represent one of your ReLU units, but you get all these other benefits which were not sort of engineered. We didn't do it by design. We just found it after we had these chips and we started using populations, which is a nice thing. Of course, now it's obvious. We know that biology does it, but it's something we stumbled upon because we were engineering and building these systems that were noisy, and we were forced to confront this. So this is what I'm saying. It's a useful tool for finding or understanding why biology works in that way. And learning, I mentioned learning is the other way to remove noise. You learn away the device mismatch. And this, we have several learning circuits throughout the years. We've implemented multiple, including STDP. But there's many from theoretical physicists like Stefano Fusi, Nicola Brunel, and Christian Martins. And because they're biologically plausible, they're really easy to do in circuits. With just a few transistors, you can put that on. Once you convert, for example, with post-frequency modulation, any analog input, any input signal into spikes, then you can send these spikes into the learning synapses. And so, of course, the first thing that people ask you is, well, how about the benchmark with MNIST? You know, computer vision, people live and die for benchmarks. And so we tried also, we said, we want to train one of our silicon neurons as a simple one-layer perceptron, like, you know, Rosenblatt type perceptron, to recognize 3, fire a lot when it sees a 3, and not fire when it sees all the other digits. And we took, you know, standard approach. We took the data from the data set. We had a high teacher signal when we had the right class and a low teacher signal when we had the low class. We trained it, we checked, okay, the accuracy was below 40%. It was like 32, 35%. So NeurIPS would kick us out. They would say, this is laughable, you know, don't even try to discuss with us. We're not interested.
Well, what do you expect for one neuron?
Exactly. Well, it's also particularly very, very noisy. I think Jan LeCun shows at least 70% with a one layer. So here we have less than 40%. So it's really laughable. And that's the reason is that our synapses have like 2-3 bit precision. Every synapse is slightly different. So if we set, I don't know, a time constant on one, the other time constants will vary by 20%. So it's not surprising that it's really a crappy classifier. But we found from the 90s, from MIT, Shapiro et al. were saying, you know, there are these boosting techniques that show you that if you have weak classifiers, like our crappy classifiers, but if you have many of them, the error goes down exponentially with the number of classifiers. And so we tried out this theory. We just said, you know, we have 256 neurons. Let's just add more and more. We send exactly the same input to all of them. They will all be different because the neurons are different. So they're very different weak classifiers. And you can see as you go from 1 neuron to 2 to 4 to 8 to 16 to 32, your accuracy goes up. In our case, it doesn't go up exponentially because there is some correlation. There is a gradient in the chip, so they're not completely independent, these weak classifiers. But we do we are compatible with the theory that is showing that, you know, populations of units of classifiers do better, or ensemble techniques do better than single neurons. We were also wondering, why does this not work? Why don't people use it on standard ANNs with GPUs? And the reason is that there is no variability. These weak classifiers are all identical. So if you have 1 or 1,000, it makes absolutely no difference. And so again, this is a place that shows you this theory that was proposed many years ago is not actually exploited because people don't have noisy neurons. Maybe if they add noise, they could improve it. And maybe random forests or other tricks exist that do take advantage, but the standard backprop approach doesn't. You had a question.
Scaling works out well if there's negative feedback, right? If there's an error improvement. Given it doesn't seem to follow that exponential tail, is it more of a central limit thing where you get averaging, statistical averaging?
I haven't checked. I haven't tried to understand the details of why we don't get this exponentially rising. It could be that it's a central limit theory. Yes, Olivier.
Dynamics of the synapses that you have here.
The synapses are first order low pass filters. So you have a spike coming in and you have a decaying exponential. Yeah, and you can change the time constant and you can change the weight of that. Yeah. They're passive, so they're basically just a capacitor and 2 or 3 transistors. There is no amplifier, so if there is no spikes, there is no current flowing, there is no power being burned. So that's the nice thing about these chips. If you have biosignals, that are quite static for seconds, nothing is burned, and only when you have a peak coming in, if you encode it with a sigma delta, then you see something change, and then you charge up a capacitor, and then the power itself is just the capacitor discharging. There is no static power being burnt at all. Imagine if you have a GPU or a microcontroller, you have a clock running all the time, whether you have data or not, you keep on doing cycles and burning power. Now, to show you an example of a learning circuit that was just recently fabricated, my students are testing it in this very moment. We have a chip where we have populations of neurons that are excitatory, that we call pyramidal, that have also 3 compartments. There is the soma compartment, and then these first-order low-pass filters go through a sigmoidal nonlinearity. We call that the basal compartment. And then another one goes through a different sigmoidal nonlinearity. We call that the apical compartment. So there's basically these 3 compartments, and we can then send spikes to the basal synapse, the apical synapses, the basal synapses, and we can connect the neurons in different ways. We can also connect neurons with excitatory synapses or inhibitory synapses, and depending on whether these produce inhibitory connections or excitatory, we call them in different ways. The excitatory ones are pyramidal. Typically, we were only using PV type of inhibitory cells, but we found out that by adding 2 different time constants to the parameters and calling them with the SST and VIP names, we could actually improve learning a lot. I'll show you how it works. This is a circuit that is always on the chip. Imagine it's a robot moving around, so there is no one telling, now you have to train, now you have to do inference. It should understand on its own whether it should be in training mode or inference mode. And so the way it works is that as soon as you have some attention signal together with the teacher and your input, you can train the synapses. These are the inputs coming from the sensory inputs, and then you can change the weights of those synapses. The reason that you can do that is that you basically, what you do is a Hebbian learning rule. You see if my input is low and my teacher is high, I should increase the synapses. I'll show you. And if the input is high and my teacher is low, I should decrease them. But you need to send the teacher information to the soma. The context attention signal allows this signal to flow through because it's blocking the SST cells. So it's a disinhibition that blocks the SST cells. So if you have attention, you can learn. This would be your training mode. As soon as you remove the attention signal, the VIP cells are not on anymore, and SST cells are active because they receive some excitation. And so they block the apical current, and so you cannot learn anymore. They also decrease the average activity of the pyramidal cells. So the pyramidal cells go into inference mode. And it's all done just by having external spikes through this attention or context or prediction signal or not. But the learning algorithm is always on. And if it's not blocked, it will change the synapses. And if it's blocked, it will not change the synapses. We have the circuits. All of these things are actually electronic circuits with 3, 4, 5 transistors each. Whenever you receive a spike through this low-pass filter, the spike is a pulse, but the output of the low-pass filter is a current. So this would be the apical current. On the bottom, you have the basal current. You create copies. You sum them together because they have to excite the neuron. They both go with plus signals to the soma. The soma integrates them and then fires. We also have another integrator that calculates the equivalent calcium concentration, or if you want, the average firing rate of the neuron. And then we take the difference between the apical and the basal to calculate the weight. The weight basically is saying if there is a positive difference, increase the weight. And if there is a negative difference, decrease the weight. So this circuit here is always sending out the signals to increase or decrease the weights. And it will change the synapses by using these currents. And it only does that if you have enough calcium activity, which is coming from whether you have the SST blocked or not. So this is like a third factor that this is a Hebbian term. You have a learning rate, and then you calculate the difference, pre and post. And then there is a third factor which says stop learning or allow learning. And all of this, as I told you, it's basically 5-6 transistors each. It's really, really easy to implement this using this Carver Meets type of approach. We now did the simulation where we have, let's present two patterns, binary classification A and B. We split this population of neurons in two clusters. So it's the same circuit, we just split it in two. Instead of 32 neurons, we now have 16 and 16. And then we send pattern A to one cluster and pattern B to the other cluster. So we want the first cluster to learn to recognize pattern A, to fire when it sees pattern A. It's like, a vertical bar neuron. And the other one to be a horizontal bar neuron whenever it's pattern B. And so when we first initialize everything, they're all identical. The weights are the same to both clusters. And so if you send in A and B, they overlap. You don't see the blue because it's under the orange. When the initialized identically, they fire identically. And so A and B are the same. But when we turn on learning, we send the attention signal. We start to see the difference between A and B. The weights change. The wrong weights go down. The correct weights go up. The overlapping weights, there's a weight that is shared by both, stays more or less in the middle. And when we turn the attention signal off and we redo the experiment, at this point, you do see the blue and the orange differentiate each other. So this is just to show you that it actually works. And this data here is data with silicon simulations. It's done on Cadence with transistor equations and everything run through Cadence. So it takes actually a whole night to simulate 2 neurons and 3 synapses per neuron. So this was very, very CPU intensive. But it's actually faithful to what's going to be on the chip because it's really circuit simulation of with noise and device mismatch and everything. We did the same experiment where we put all of these equations into a spiking neural network simulator, not a circuit simulator, a high level behavioral simulator, which is called NEST. I don't know if some of you use it. In that case, we could have hundreds of neurons and tens of synapses. And so we did the same experiment with that, in which, remember, there is a subset of the synapses that are receiving input to both A and B that are overlapping. So those subsets are more or less blue, but the other ones become yellow and when they should be yellow and black when they should be black, and vice versa. So this binary classification works also with the whole population at a higher level abstract simulation framework. So this is just to show you that by using these circuits, you can do these types of systems that can learn, and then you can use those either in implanted devices inside your body, or in where you need very low power in rooms if you need to count people, or if you need to monitor avalanches. Anywhere you have a very small data set. Anomalies are by definition not very popular, so there is very little data for them. And if you need to have low power, you don't want to change the battery every year. If you implant a pacemaker, you want to change the battery every 7-10 years. But if you put things in mountains, also you don't want to go every week to change the battery. So in that case, this approach can work. Exactly. So you have the advantages of being compact, low power, low latency, but they don't scale well, I told you. They are very, very noisy. Even in case of binary classification, or MNIST classification, you get 30% with one, but if you have like 100 neurons, you still get like 80%. You don't get 99.99% that people that do AI are looking for. And so they're low accuracy. So they're not meant to replace GPUs. They're meant to complement them in places where GPU is overkill. It's overkill, and maybe it's just burning too much power. So they're good in closed loop sensory systems. Sorry for this. They're good in multimodal sensory fusion. Any signal that can be converted to spike can then be classified, whether it's auditory, visual, pressure, temperature, IMU, and so on. And you can use them for always-on learning. So you can have learning always on without worrying about power consumption. And yeah, as I said, I wouldn't use them. If you have digital data stored on a USB disk, on a hard disk, you might as well use a standard CPU. You shouldn't use these technologies. These are good for intelligent sensors. If you have a sensor that you need to connect to an intelligent processor, then this is okay. But if your data is already digital, you might as well use a GPU or a CPU. And there are still challenges. So I showed you how to use populations to do robust computation, but still neuroscience can help us understand how to improve that even more. And the biggest challenge is how to program these. How do I create an if then else loop with a bunch of neurons? There are theories on how to solve Sudoku problems, how to do reasoning, but it's not like a Python program that you write. You really have to think of how to connect these elements, these dynamical systems together to reason through a problem and to solve a problem. So this is still something that is not a problem of engineering, it's a problem of co-design with theoreticians, computational neuroscientists, and software and electronic engineers that can build a system that can do that. Finally, neuromorphic is dead. This term I was provocative, meaning that it's being used in too many different ways. But I hope I convinced you that the original still has value. So these old timers that still cling on to the original definition can do useful things. The idea is that if we combine this old school neuromorphic engineering with all of the neuro AI ideas that are coming out, there is hope that we can really better understand the brain, but also build systems that can really complement standard AI in places where standard AI is not optimal. These principles of neural designs are the classic ones, that any neuroscientist knows, to emulate the physics, co-localize memory and computation, maximize the parallelism, compute through time, and use populations of slow and heterogeneous elements. This is actually a feature, and it's not a bug, like it was thought for so many years. And more papers, especially in the last 5 years, are coming out also from software simulations showing how adding variability, heterogeneity, improves accuracy in computation. And also the other one I didn't write here, but it's oscillations. More and more papers are showing how you can improve on MNIST benchmark if you have oscillations in these networks. I'm collaborating with Wolf Singer and Earl Miller, actually, and we try to put this on these chips as well. So with this, I would like just to acknowledge the group, which is here. There's very, very talented postdocs that have been helping throughout the years, but also with these latest results. And throughout these years and collaborations, there's been many students going through both INI and INC, and also the collaborators.
And the upper right-hand corner, are those the
I
dead
just put the
students?
audio to the
Well, this is
to the class.
it was an attempt to write NCS for neuromorphic cognitive systems on the snow, but yeah, they didn't get up anymore after that. Yes, and thank you for your attention.
More questions?
Thank you, Professor Indiveri, for a very nice talk. You mentioned one of the challenges being the way that we program the systems. And I see that the way that SNNs are being used right now is just a conversion from ANN to SNN mainly. Do you see the neural engineering framework proposed by Eli Smith as a way to bridge this gap?
Yes, there are several frameworks that can bridge this gap. The one on pointer, what does he call it? Semantic pointers is one. It hasn't been brought forward since when it was first introduced. So now there is actually different, newer types of approaches that are being proposed. I like more the ones on recurrent neural networks and looking at dynamics and manifolds and trying to see what you can do in the lower dimensional states. But as I said, it's an open problem, and there's no clear solution yet. So yeah, anything that can help is useful. So also the Chris Eli Smith's framework is something that we could go.
So the brain's quite a bit more messy in its signals than these transistors. So do you think there would be any benefit in implementing things that represent local field potentials or neuromodulators like serotonin, dopamine?
There are, we do use, so as I said, there are these side circuits that set the parameters, because every circuit has a time constant, a refractory period, a spiking threshold. All those are hyperparameters that are set on the side with these temperature compensated circuits. But those parameters can be changed online as the activity goes on, as the dynamics goes on. There could be a computer that's basically checking what is the average firing rate of the neuron. If it's going down or up, I can change the threshold of the neuron without interrupting the dynamics. And so with the computer in the loop, you could have neuromodulators that change the activity of the neurons, maybe with some homeostatic algorithm. So there is space to play with these chips and explore these ideas, but we do need a computer in the loop for this. Of course, once we find something that works, maybe we could then design a chip that has that circuit in the feedback loop. But when we still don't know what we're looking for, the best is to add the flexibility of the computer in the loop to change those parameters.
Very cool, thank you.
I have a question for you, Giacomo.
Yes.
Really great work. Now, one of the items that you mentioned as a con for neuromorphic is that it doesn't scale. I would probably give an existence proof that definitely does scale, because our brains are really great at what they do, and they definitely scale as far as more connections in our brains than in many of the supercomputer systems that exist today. So there is an existence proof at least.
No, I'm saying that it's just difficult with this technology to scale them up to, I mean, it's expensive. I shouldn't say it doesn't scale, it's just costly to make these chips scale. But as I said, maybe as soon as we can start to use the 3D,
yes,
which is, what you're working on together with the Stanford group, maybe we can really build large scale systems.
yes, or hybrid systems where digital
networking, and of course,
application, and then you have
and even maintaining. I would put
put
another RISC processor to the side just to maintain operations parameters and other things. So combining really digital and analog and memory-stive technologies, I think, is the way to go.
Do you have a startup company?
The ETH has said many, but the one that my postdoc made a few years ago, actually in 2017, is called SynSense. And they do these edge computing low power chips. In the end, they merged with innovation. So now they do vision plus spiky neural networks. My postdoc was Chinese. We got money in Switzerland for 2-3 years, but then it was 2019, it was COVID. And it was very hard to find investors in Switzerland. But as soon as he said, I'm doing neuromorphic in China, he got buried with money. So he moved the headquarters in China, but the research development part is still in Zurich. My postdocs and his employees are there.
So I read somewhere that there are like dozens of startups in neuromorphic, and I know the DDS.
Thousands.
1,000?
No,
I know a few, a handful, but there are starting to be more and more. So it's a good sign, I think. It's good to be in a competitive. It pushes progress.
Okay, what's the killer app going to be?
As I said, the edge computing, anything where you need to have something that is small, that is always on, that needs to always look for things happening, and that doesn't require very, very high accuracy or very, very high complexity in the learning. So something that you can do with a perceptron is ideal as a killer app. And the body is one example. So we're going to have the NER conference starting tomorrow. So there's going to be neuromorphic workshops, neuromorphic sessions. That's one killer app. Also, is basically implantable devices that need to be low power and need to have low heat density. If you think about it, putting it on your cortex, you don't want to fry your neurons. So you need to have very, very low power circuits there.
What about robots?
That's the other one. It's more difficult because the roboticists are very, very conservative. So they want to have, I want to move my arm by 32.7 degrees. I don't want to have something that's noisy and they want to have like a cluster they'd rather have a cluster on the side of the room that controls the robot. So it is something that's going to happen, but I think it's going to take longer years because of the communities, the different philosophy in the roboticist, classical roboticist communities and others. The one that is the most promising is the one working on soft robotics, where they deal with messy stuff and they are more open to trying out crazy ideas.
Well, let's compare the best, say, robot dog, from Boston Robotics, with a real dog. There's no contest.
Yeah.
It's like, nature has been there for hundreds of millions, they're talking about, evolution has created bodies which are, and you're talking about, we don't count how many degrees our moves, right? I mean, we kind of approximate that.
Yeah.
And we've nature has found ways of being very flexible and very, very ability to, like a cat, to do amazing acrobatics.
Yeah,
right?
robotics.
I mean,
But also computer scientists, when we talk about our chips to computer scientists, for example, I'm working with colleagues that work on brain-machine interface, body-machine interfaces. The AI approach is to have a deep network, to train it on a large data set, and then to control, like you want to control the angle of your prosthetic fingers so that you can get an egg or a glass of water. And they fight over 1 degree or 0.5 degrees, but humans cannot distinguish below 3 degrees. So what's the point of putting all this power in something that, is not necessary?
Well, it turns out compliance, the secret is to be able to adjust and when you press something, you have to have an idea of how much it weighs, you have to have an idea of how much it's going to grip, friction.
And then providing sensory feedback to the
And it's all about
patient.
control theory.
Yeah.
It's putting controls into it, not just,
Yeah, and the AI approach is to do this ballistic, precise thing.
open loop. No, that's not the way to control body.
So we need biomorphic robotic before we can have neuromorphic control.
Yeah, it's coming. There are colleagues that are working in that field.
There's a question over there.
Okay,
Okay.
maybe one comment and then a question. The thing is that if you compare it with MNIST, it's not fair because it's classification with a static and there's no dynamics. And then you have spiking neural networks or, your neurons that are dynamic. And so you're using a much more powerful system, the dynamical network to actually just solve a static problem. And so I think that maybe the hand gesture might be a better thing. But the other thing also is that I think it's you name this noise on these neurons. I don't think that's noise, that's variability.
Yes,
right?
it is. Yes.
And so the thing is that points out that the problem is not with the neurons themselves, but it's with the learning algorithms. It's the learning algorithm that has not taken into account the change of each neuron. But if it can, then you can actually use it fully. And I think that if you use and I worked on this, if you use on some optimal control theory, you can actually leverage each neuron individually and to the maximum power they can. In other words, you're an orchestra and each are doing their own music. And you need now the conductor to actually point when each has to come and participate. And that's the issue that's missing. And I think that it's possible to actually get the same accuracy as you have with a GPU, but with those systems. It's just that the learning algorithm is not there, but we do know it.
Yes.
Actually, part of it has been developed in Terry's lab. So, and then the second thing is that in these electronic circuits, what we know, all right, there's another thing is, so in the brain, we know that if you did the regular experiment, you had all these fuzzy answers. But also in Terry's lab, if you show that you use natural stimulus, you actually get this spike at exactly the same time. So there's very little variability, but each neuron kept the same time, exactly like you have in your circuitry. So in your brain, it seems to be a lot more like in your circuit to be a lot more in your brain, but in the brain, you use a different learning algorithm. And the beauty of it also is that if you use optimal control theory, you find out that you recover an STDP rule that comes out of the optimal control theory, plus something that is a reward, but it's not a reward for truth. It's actually determined by the exact participation of that neuron into the overall output of the network. Now, question is that I've worked on a theory that actually simplifies a lot spiking neurons, for example, for different under threshold dynamics, so that in circuitry, typically people like at BrainChip, for example, implemented one where you can only insert 100 neurons because they try to reproduce each channel dynamics independently, the equivalent channels of neurons, right? And that's not possible. But there's a theory to actually summarize this and make it easier. But in the circuitry, how can you go beyond the decreasing exponential in the diversity of dynamics? Is this something that's as difficult to do or it's easy to do?
No, I would say it's, so for this last question, I would say it's relatively easy to do. If you know any first, second, third order differential equation, it's quite with the not huge dynamic range, it's quite easy to implement with these current mode circuits. So if you do have the equations for a more complex synapse, which is actually a proposal we were working on together with Stefano Fusi for these metastable complex synapses. It's possible to do the circuits. You pay because the synapse is really part of this matrix. It's taking up all the area. So the more transistors you put per synapse, the area increases, with the square. So you pay for it, but if it's beneficial, if the cost benefit is positive.
How much of it is using the pure analog circuitry of the system?
All of it is all analog. It's there is just one transistor that's converting the pulse into current, and then the rest is all analog. Yeah. And for the MNIST, I would argue that, we looked at this, we put ourselves in the worst case scenario. It's the wrong way of using these neurons because they're dynamic, but we just, gave a static input. We waited for everything to reach steady state, and then we took the average firing rate. So it's, we do have gesture classification, and you're preaching to the choir here. It's, we do have things that with the best way to use these is to use spatial temporal signals, and to really get the best advantage of the dynamics that you have. And so the colleagues working on biosignals, they do EMG, ECG, and they do prosthetic control. So that's really the best place where to use these. MNIST is just only because reviewers ask for it. Otherwise, we would never be interested in doing MNIST benchmarks.
Okay, well, thank you for a great inspiring talk.
Thank you.